Okay, so when we look at now the gold leaf experiment or the scattering experiment in more detail, what we will begin to what we need to be able to do is to explain the experimental data in terms of what was found and how that actually proves or indicates more favorably the nuclear model that we have today. So let's look at this particular setup here, and we'll break this experiment down into its parts. So what we have here, we have the gold leaf experiment set up here. So you can see here where the gold leaf has been identified, and you can see here that you've got a detecting screen around the outside edge, and then you've got your alpha particle emitter or your radiation source by which the alpha particles will be fired in a beam towards the gold leaf, and then you would get your subsequent detections based on the trajectory of the alpha particle. Now, what you can see here is that the beam is, let's put it in a different color so it's more better to see. We can see that the beam here, so let's take that as A, okay, is quite pronounced. Now, this is important because this is actually supporting, in one sense, the plum pudding model, because the majority, so let's say the majority of the alpha particles that are fired towards a gold foil, they pass straight through without any deflection, no problem at all. However, what you're starting to get here, in these regions, you're seeing that the alpha particle is bending. The trajectory is slightly curving, or it's not following a straight trajectory. It's not going straight through. And even more significantly, these trajectories, i.e. when there is a deflection or bouncing back of the alpha particle, is suggesting that the atom is holding more secrets, or there is something else there that the alpha particle is interacting with. So the scientists had to break down these observations and try and explain out what they were actually seeing, or what these data points correspond to. What does this mean for the structure of the atom? And that's what we're going to do now. So let's go forward. Now, this is essentially what is happening at the atomic level. Actually, before we do that, let's take a look at this experiment here. So here we can see, now before we go and break down the plum pudding data and explain away how the atom comes about, I just want to take a step back to the plum pudding model. Now, if the gold leaf atoms, or the gold foil that is where the alpha particles were fired against, if the atoms were like this image you're seeing here, i.e. the plum pudding model, a spherical kind of positive region with negative charges dotted around, and if we scatter alpha particles like this towards the atom, this is the trajectory that the alpha particles should have taken. So here you can see those small alpha particles fired at the gold leaf, and if the gold leaf atoms were like this, i.e. a positive sphere with negative charges dotted around, the alpha particles should take this trajectory. As you can see, there are no deflections. They pass straight through. This is what was hypothesized with the plum pudding model. So to the left, you can see where I'm switching off and on the alpha particles. So I'm switching on the alpha particles. They're fired at the gold foil, and this is what was expected. If I put tracers on to the alpha particles, you can clearly see that they are not deflecting. So this is what was expected. However, in reality, we got something quite different. So if we look here, so here we have got the nuclear model of the atom, and when we fire the alpha particles, here the alpha particles are being represented as the purple dots, where they're not showing the 2 protons and 2 neutrons. However, they do show the nucleus in the center orbit, and we have electrons orbiting the nucleus. And as you can clearly see, if I just slow down the energy of the alpha particles, what you can see is that there are clear deflections, bending of the trajectory, and in certain instances you can see that the purple dots or the alpha particles hitting the yellow dot and bouncing back. Now this is what the gold leaf or the scattering experiment was showing. Now if I put the tracers onto these alpha particles, you can see it matches the gold leaf experiment diagram that we were looking at previously, where the trajectory of the alpha particles have changed due to certain influences. Now if I was to show you here, again we can take another approach for this. We can see again alpha particles being accelerated towards a gold nucleus, and as they come close to the gold nucleus, you can see that there is an alteration in their trajectory. Now you should be able to understand why there is an alteration in their trajectory if you go back to the previous slide. So if we go back a few slides, and where I talked about the alpha particle and how it would be important, I said that the alpha particle is positive, has a positive charge, and any nucleus of any atom also has a positive charge. So what you find is that when you bring 2 positive charges close to each other, there is going to be a repulsive force. There's going to be repulsion. So as the alpha particles get too close to the nucleus, there is a deflection in the trajectory of the alpha particle. So how can we explain this? So now we need to be able to explain what we're seeing in terms of the trajectory of the helium nucleus of the alpha particle. So the gold leaf experiment has indicated to us that most of the alpha particles pass straight through. Now we should not dismiss this. This is very important for us because most of the alpha particles have passed straight through. This means that most of the atom is empty space. Most of the atom is empty space. That is why most of the alpha particles pass straight through. A small deflection, this indicates, let's put it in a different color, the small deflection, i.e. the curving of the alpha particle trajectory, this indicates that the nucleus, the nucleus is positively charged. So the deflection, i.e. the repulsion, occurs because you have a positive alpha particle and a positive nucleus. So when you bring two positive charges together, there is repulsion and a small deflection is felt there. Now, then you have a large deflection. This occurs when the alpha particle gets close to the nucleus. So we get close to the nucleus here. So the alpha particle has got close to the nucleus. So large repulsion here. Now, in terms of percentages, this would be the most. So we would have this being the most. So most of the alpha particles passing straight through, that was what the majority of the results were showing. Then in terms of, again, let's say percentage-wise, what results they were getting would be here, a small deflection. So a few of them were getting close to the nucleus and repelling, and the alpha particles were showing a deviated trajectory. Then, in terms of abundance of results and data, they were getting the large deflections. So if we were to take it out of 100, let's say, again, these are very rough numbers. I'm just exaggerating the numbers just to show you. Let's say here we have 80% detection here. And let's say 10% detection here. And let's say 5% detection, or let's just say, 5% detection here. And then we take our last, let's say our last ones, which is let's take the last one. We have, let's take this as our D. Turned back, this is where the alpha particle has hit the nucleus. So it's actually hit the nucleus and it's deflected back out and hit the detector in the front half of the scattering ring. And in terms of percentages, less than, so this is less than 5% in comparison. Okay, less than 5%. Now these are all approximate values. These are not exact values. These are just approximate values just to give you an idea of the results that were obtained. Now, so if less than 5% are hitting the nucleus, but we are getting a significant amount, we are getting a detectable amount of alpha particles being turned back, this indicates to us that the nucleus is very small and it must be centrally located. It must be centrally located. I'm not sure if that's a double L. Okay. It must be centrally located. So what the gold leaf experiment has shown us is that the nucleus must be positively charged because the alpha particles are being deflected or their trajectory is changing either a small amount or by a large amount depending on how close they get to the nucleus. So the nucleus, if it's repelling the alpha particles, it must be positively charged. Sehowever, we can make another conclusion as a very small percentage of the alpha particles are hitting something and bouncing back. We can infer from that the nucleus must be extremely small and centrally located. So what does this mean for the 80% of the alpha particles that are passing straight through? It must mean that the atom is mostly empty space. So the atom must be mostly empty space. That's why we get a large percentage of the alpha particles just passing straight through, not being deflected by any charge or hitting anything. So this was just a summary of the gold leaf experiment, of the history of the atom, and how we have come about to this nuclear model of the atom. Now this will be important for chemistry and for physics. Now you will need to know this for your physics in addition to your chemistry.